We often treat vector spaces as abstract playgrounds, but to measure lengths and angles, we need an inner product. Today, we're looking at the properties of positive forms, the requirements that determine how a vector space gains its geometric shape. A sesquilinear form is a function that takes two vectors and produces a single scalar value. In this setup, the function is linear in the first slot and conjugate linear in the second. When focusing on positive forms, we want these scalars to behave like physical distances, where measurements cannot be negative or imaginary. Defining positivity is the transition point where abstract linear equations begin to represent the constraints of physical geometry. Take the Hermitian requirement. F of xy equals the conjugate of f of yx. If we plug the same vector into both slots, the output must be a real number. This is a prerequisite for positivity, as inequalities only make sense if the numbers aren't imaginary. To function as an inner product, the length squared of any non-zero vector must be greater than 0. The form remains strictly positive unless the vector itself is 0. To calculate this for a specific basis, we translate the abstract function into matrix notation. The form is now expressed as y star times matrix A times x. Testing every possible vector to prove positivity is impossible. Theorem 5 offers a different approach. If we can factor our matrix A into p star times p, the calculation becomes the dot product of the vector px with itself. Squaring a term like this ensures the result never drops below 0. We can also verify positivity through Theorem 6. This involves checking the determinants of the first, second, and third top left submatrices. If these principal minors are all positive, the entire matrix is positive. Let's apply these tests to a 2x2 complex matrix. The entries on the main diagonal are real integers, 2 and 2. Looking at the off diagonals, we see I and negative I, which are complex conjugates. The matrix is Hermitian. Try calculating the principal minors yourself. The 1x1 minor is just the top left entry, 2. For the 2x2 determinant, we have 2 times 2 minus I times negative I. That's 4 minus 1, which is 3. Both are positive. Passing these specific tests proves this matrix defines a valid inner product on the space, allowing us to use it for geometric measurements. Matrices are one way to look at this, but we can also use linear operators. Every form corresponds to a unique linear operator, T, embedded within a standard inner product. A positive operator must satisfy the same core logic. It must be self-adjoint, and its inner product with any vector alpha must be greater than or equal to 0. Theorem 13 shows us that positive operators behave like positive real numbers. Each one possesses a unique non-negative square root, n, where n squared equals t. The math on the left shows how a non-negative real number x yields a real square root. On the right, we see the same behavior in linear algebra. A positive operator t yields its own square root, n. We can extend this logic to complex numbers. Any complex number can be expressed in polar form as a magnitude, r, and a rotation, e to the I theta. Linear operators follow this same pattern. We can break them into two parts, a positive square root that handles stretching, and a unitary operator u that handles the rotation. Recognizing positive operators allows us to break down complex transformations, revealing how they stretch and rotate just like the numbers on a complex plane. We began with an abstract definition and found that positive forms provide the structure for all geometric vector spaces. By using the p star p factorization, or the principal minor test, we can verify this structure through direct calculation. At the operator level, these forms mirror the arithmetic of real and complex numbers, proving that even abstract operators follow familiar geometric rules. Thank you for watching. To explore these proofs in detail, refer to the foundational text by Kenneth Hoffman and Ray Kunze.